Okay, let's have a look at the logistic model. So let's start from our original Malthusian model, the one where we have dn over dt is equal to r times n. And we now consider that there is an additional term, a term of loss of individuals, where m of n represent either a reduction on fecundity or an increase in mortality. Now, let's assume that this term is actually proportional to the density of the individual times a parameter gamma. So we can rewrite our equation as dn over dt is equal to Rn minus gamma n times n. That means basically this is minus gamma n squared. We can now gather model parameter as represented here in these equations, where we get Rn, which is the same component we had in the Malthusian model, that multiply terms in the brackets, which is equal to 1 minus n divided by r divided by gamma. And we call r divided by gamma k, that correspond, as we have seen, the carrying capacity of the population. In fact, you can see here that basically dn over dt is equal to capital Rn times n, where Rn is the per capita intrinsic growth rate, which now is constant any longer, okay? But it actually happened to be a decreasing function of the population density, and it's a linear function. It's the equation of the straight line that for n equal to 0 is actually, let me do that here, is equal to r when n is equal to 0, it's just little r, and for n equal to k, these terms in the parentheses is equal to 0. And so for n equal to k, the intrinsic per capita instantaneous growth rate is equal to 0. Let's talk about equilibrium. Equilibrium means that there is no change in population density with respect to time, right? So the way we can compute it is by setting dn over dt is equal to 0. Okay, so I give you 20 seconds to think about what are the equilibrium points of this model. And I already give you a suggestion because this model actually has 2 equilibrium points. So think about that. So probably, you've seen the graph that we had before. Let me actually go there. We've seen that when n is equal to k, the term in the parentheses is equal to 0. So for n equal to k, we have r times 0 times n, which is 0. That means dn over dt is equal to 0. And so for n equal k, the rate of changes of n over time is equal to 0. And yes, that is an equilibrium point. There is another one. Did you guess what it is? Well, it's actually n equal to 0. It's good. This model does not have spontaneous generations. If I start with 0 individual, I will keep having 0 individual. Okay, even resources would be available, but there are no individuals for reproduction. So now the point is at which type of equilibrium of these. And so we want to, within this video, at least the video class, the formal derivations by linearizing the system around the equilibrium point, computing the deviation, the dynamics of the deviation with respect to the equilibrium point, and showing whether those deviation increases, the perturbation increases in time or decreases in time. From a much more qualitative point of view, and I know that a lot of applied mathematicians and theoretical ecologists do not like this sort of a physical representation, like here, this sketch, but it's pretty good anyway, and I think to show that that equilibrium that is stable to understand is like the really depth of a valley, right? So that is an equilibrium point, and if there is a little perturbation from the equilibrium point, our ball will oscillate and tend to go back. So there's going to be damped oscillations in this specific, sort of a, cartoon case that will, for which the ball will tend to go back where it started from. A neutral equilibrium is like a ball on a flat plane. If we kick it a little bit, it's gonna move somewhere else. There's gonna be some friction, so it eventually stop somewhere else. Okay, it's not gonna be a track and go back. And then a stable equilibrium point is like to be at the very top of the hills of a mountain, and so a little perturbation actually is gonna bring our system away from its original state. Okay, so this is just as a simple classification of the equilibrium point. So, let's look at in order to understand what are the equilibrium, we are now drawing here on this graph the relationship between dN over dt as a function of population density. I just want to mention, and I do that there, as you see, that what I'm plotting here on the vertical axis is the function Rn times 1 minus n divided by k, which is so that we wrote this as Rn minus gamma n squared. Okay, so if there is an n squared there, the rate of change of the population density, that means is represented by a parabolic function, right? This parabolic function is equal to 0 for n equal to 0, and it's equal to 0 also when n is equal to k, right? Because for n equal to k, these terms here in the parentheses is going to be 1 minus k divided by k, which is 1, so 1 minus 1 is 0, and so it's going to be equal to 0. That means we got this parabolic function, okay, that we represented before. And as you see here, we have these two equilibrium points, what is called, the trivial equilibrium, which is if I have no individuals, there's not going to be any dynamic there to describe, and the carrying capacity, okay. And this parabolic function represents the rate of change of the population in time, okay. So if the n over dt is positive, that means that the population tend to increase, right? The rate of change, I have more individual at the next time step than I had today, okay? And but if, we exceed k, the carrying capacity, the n over dt will be negative. So I will have fewer individuals tomorrow than I have today. So the red arrows here represent the fact that on the left of the carrying capacity, the rate of growth is positive, and so if there is a perturbation from the carrying capacity, the population will tend to go back to the carrying capacity. And the arrows is pointing to the left, where if we are on the right side with respect to the carrying capacity, that means if we exceed carrying capacity, the population will decrease and will tend back to the carrying capacity. So basically, these tell us that the equilibrium of n equal to 0 is actually an unstable equilibrium point, okay? And if there is a little perturbation, if we introduce enough individual in the population, this will tend to reproduce an increase, initially faster and faster, reaching a peak, and then going down and going to the carrying capacity. On the other hand, K, the carrying capacity, is an attractor, and it actually turned out to be a stable equilibrium here, because if there is a perturbation with respect to the carrying capacity, the population will tend to the carrying capacity. A classic question in ecology, as well as in fishery management, is when the population rate of growth is going to be fastest. For what value of population density our population will grow with add more individuals or more biomass, depending upon how we describe the individual. So, we have already draw the graph representing the population growth rate, and it clearly, the distance from the horizontal axis represent the rate of growth of the population. So these obviously represent the peak. So one good way to do that is, for instance, if we have the analytical formula of the rate of growth of the population, we can compute the first derivative, set the first derivative to 0, and in this point, this corresponds to the maximum growth rate of the population. Okay. One interesting aspect that can be proven, not even too difficult, but it takes some steps, and we kind of skip them, is that the logistic growth, the classical logistic growth, has an analytical solution, okay, which is represented here, okay. So this is the function. R is the little r is the per capita intrinsic growth rate at low density, okay. K is the current capacity, and N0 is the population density at the initial, the initial density at the beginning of the simulation. Okay, so we will run some R script to show that if we start below the carrying capacity, the population will increase and tend to the carrying capacity. If we start above the carrying capacity, will exponentially decrease and tend to go back to the carrying capacity. On the other end, we said the carrying capacity is indeed an attractor, and simulation, of course, can only confirm that. Okay. Another interesting aspect that you can observe here, and it's worth paying some attention, is that this is the equilibrium is reached asymptotically in this logistic growth here in this logistic model. So there are not damped oscillations, so it just smoothly tend to the carrying capacity. And there is a second element which is interesting. We will see that is that if we start below half the carrying capacity, the population will start accelerate at the beginning, almost in exponential form, like Malthusian growth at a really low density, where density dependence is not really playing, a big role. But eventually we start to slow down. So there is an inflection point here for half the carrying capacity, for which the curvature of the trajectory goes from upward to downward, as is being represented here. So for which value of density there is an inflection point or equivalent to the maximum population growth rate. You can derive it analytically, as I mentioned, and the way of doing that, you take the equation that represents the parabolic function, you take the first derivative and solve it by setting the first derivative equal to 0 and finding what values of density reach the population growth rate is maximum. As I mentioned, I anticipated the result here. It's half the current capacity. We're gonna see in a moment a few variations of the logistic growth for which that is not actually the case until I let you do the computations and the analysis there. I want to add a caveat on the concept of equilibrium and stability in ecology. So the equilibrium and stability is a pillar of population ecology, and it's very powerful and very important. We also need, though, to be aware of the limitation of this concept. The sketch that is reported here shows that there is an intersection point between birth rate and between mortality rate, and there is a point, there is an exact density for which there is a balance between birth and death, and we said that this is an equilibrium point. This is correct. When we go in the field and we monitor the population abundance, we face a number of challenges. First of all, especially for fishery, it's extremely difficult to have a reliable estimate of what the population density is, because in a lot of cases, especially for fish, they are underwater and they're mobile. And so there is a science per se. We're going to see something along the course that is about stock assessment, and it's not at all trivial. And understanding what is there is difficult. And the point is that it's affected by uncertainty, and sometimes by a lot of uncertainty. So, what is the stock exactly is difficult to be said. Second point is that there is a lot of environmental variability. Our model is a deterministic model. Okay, does not even account for the stochasticity, but in the reality, there is no year that looks the same. There might be more variables, and here there are less variables. So there is a lot of variability there. The fact that these models are single species model, while a population is usually embedded in a food web. We're going to see that in about a couple of weeks and see what is the effect of being in that food web. So not only our population is directly affected by the vagaries of the environment, for instance, or other form of anthropogenic disturbance, but they are also affected by, the fluctuations in their own resources and in their own predators or competitors. And so these all together, basically lead to the fact that, when you look at there, it's actually really difficult to see a single carrying capacity, and probably a more realistic graph is the one that I reported here, in which the idea is that there is a lot of uncertainty about what is the actual mortality and the actual birth rate given a population density. And so rather than a carrying capacity as a single precise value, even if the population is truly around equilibrium, there's going to be a range of density around which the population generally fluctuates. Okay. A few considerations about parameter estimation. I just want to mention upfront that the best way to estimate the known parameters in ecology, certainly in general, is to use maximum likelihood estimators. And we will see how it works later in the course. These maximum likelihood estimators, in a lot of cases, unless they can be derived analytically, we can solve them numerically, and the search algorithm that we use, might still need that we provide an initial guess for model parameter. So I want to talk about how we can provide an initial guess to model parameters that is as close as possible to the maximum likelihood estimator. So let's start again, as you can see here, from our analytical solution, and let's do some. We rename the the variable. First of all, so this solution give nt as a function of n0, so we can rewrite it here as a nt plus 1 as a function of nt. It just comes directly for that one. If you put t equal to 1, for instance, and then you reiterate this again, you will see that this is the recursive equation that is derived from the analytical solutions of the logistic growth in continuous time. And it's exactly the solution. So if we plot this on the graph that we just plot, where we integrate through time the continuous time model, we would get exactly the same type of model. Okay, and then we rename model parameters, and so we say that lambda is equal to e to the power of r, which we have seen it already, is a finite growth rate, a low population density. And then we derive a parameter that we call alpha, which is e to the power r minus 1 divided by k. And so if we do that, we can derive this recursive model that you can see here, in which n times t plus 1 is equal to lambda n divided by 1 plus alpha n. Why this is relevant? Well, because we can again shuffle model parameters, for instance, to derive these type of models, in which on the left hand side we have nt divided by nt plus 1, which is equal to alpha divided by lambda times nt plus 1 over lambda. Okay, and you see that you should recognize that this is actually the equation of a straight line where the y equal to ax plus b, where y is equal to nt divided by nt plus 1, x is equal to nt, a is equal to alpha divided by lambda, and b is equal to 1 over lambda. And r is, of course, the logarithm of lambda, and k is equal to lambda minus 1 divided by alpha. And so we can use basically, we can, compute nt as a function in t plus 1 and plot this new variable, the y variable, on the vertical axis, nt on the horizontal axis. If the population is following logistic growth, that will be on a nice straight line. We can use linear regression to estimate the slope, and the slope a, which will allow us to compute alpha divided by lambda, and the intercept, which will allow us to compute 1 over lambda. And so we can use this information to derive the initial estimates of the intrinsic growth rate r and the current capacity k. Last point I just want to mention is that there are several alternative formulations on the basic, foundations of logistic model that you can see in fishery book or population ecology book, depending on how much sophisticated they are. You can have the terms in the brackets that as an exponent alpha, or this one here that an exponent I call with a different name, beta, or even n to the power of gamma. Okay, so these are a generalized logistic model. And what I like to ask you guys is to basically plot, the dn over dt, so the population growth rate, as a function of n for different values of alpha, beta, and gamma. Okay, you can start with alpha, beta, and gamma equal to 1, and that is logistic. We know it's a parabolic function, is reach the maximum for half the current capacity is a symmetric function. What happens when alpha is larger or smaller than 1, when beta is larger or smaller than 1, and so on and so forth. Okay, so you can, and you can see what is the difference in terms of this, the population growth rate, and also, understand what are the differences in dynamics, how this is going to affect the dynamics. I also want to mention that in fishery model, there is often the habit to use this type of model. It's a classic Fox surplus production models in which it is explicitly representing the current capacity K, and then MSY, which is the maximum sustainable yield. We haven't seen it yet into the details. We're going to see that soon. And it's important. Let's represent the maximum harvest that can be sustainably removed, basically, every year, and potentially indefinitely for a really long time, some caveat. So this is, it just represents two parameters that in fishery models are really important. And so it might, be interesting for you guys to see, how, these dynamics change given MSY and given K, or, in terms of alpha, beta, and gamma. And that's it for this little model. Thank you.